Hey, ladies and gentlemen, this is Miss Humbert here, and today we're going to be talking about Notes 5, which is mutually exclusive and inclusive events. So let's take a look at an example of when we're going to be using this. So it says that a bag contains 8 marbles, or 8 red marbles, 12 blue marbles, 9 yellow marbles, and 11 green marbles. It says a marble is drawn at random, find the probability that it is blue or green. Well, first what we want to do is figure out how many total marbles we have. So I'm going to add 8 plus 12 plus 9 plus 11. And that gives us a total of 32 marbles. Well, our successes is blue and green. So we have 8 blue, and we have 12 blue, and we have 11 green. So our successes are going to be 12 plus 11. And that ends up being 23 successes over 32 because we added the amount of blue and green that we had. When you divide that out, you end up getting 0.719. So there's a 71.9% chance that you get a blue or a green marble. All right, let's take a look at mutually exclusive versus inclusive. So mutually exclusive events are events that do not affect each other. So for example, rolling a 5 on a dice and flipping a tails. Dice and coins don't affect each other, so all we have to do is simply add the probabilities, and that's basically what we did on that first problem there. However, sometimes there are events that do affect each other, and we call those inclusive events. Those are events that do affect each other. So for example, if we roll a number less than 3 on a dice or a 1, what happens is a number less than 3 and 1 could end up being the same thing. So we end up counting that probability twice. So what we have to do is we have to actually subtract off the probability of it being both. So that way that probability isn't being counted twice. This will make a little bit more sense when we get into using actual examples. But before we do that, I just kind of want to decide, okay, is it mutually exclusive or is it inclusive? So basically, can it be both? So for the first one, drawing a heart or a diamond from a deck of cards. Well, hearts and diamonds are two of our suits. They're two separate things. You can't be a heart and a diamond, so that makes it mutually exclusive. Drawing an ace or a spade. So you're asking yourself, can it be an ace and a spade? And it can. You can be the ace of spades. Ace is a type of card, spade is one of your suits. So this is an inclusive event because it can be an ace and a spade. Take a look at the next one, rolling a 5 or rolling a number greater than 3. Can you be a 5 and a number greater than 3? Yeah, you can. So that makes it an inclusive event. Picking a red or a blue M&M out of a bag of M&Ms. Can you be a red or a blue and a blue M&M? Yeah, no, you can't. You can't be two different colors. If you notice, M&Ms are solid colored. Okay, so you can't be both. So because you can't be both, that makes it mutually exclusive. All right, so let's take a look at number 5. One teacher must be chosen to supervise a senior class fundraiser, 12 math teachers, 9 language teachers, 8 social studies teachers, and 10 science teachers. If a teacher is chosen at random, what is the probability that it is either language arts or social studies? Can you be a language arts and a social studies teacher? We're just going to assume that you can't be both because there's not very many teachers that are both. So that makes us mutually exclusive because you can't be both. So here's how we're going to calculate out that mutually exclusive probability. What we're going to do first is I'm going to calculate out the probability that it is a language arts teacher. So let's count how many total teachers we have. We have 12 plus 9 plus 8 plus 10. So that gives us 39 total teachers. So there's 39 total language arts teachers. Okay, total teachers, and then there are 9 language arts teachers. So the probability of it being a language arts teacher is 9 out of 39. So now that's taken care of. Then I'm going to add the probability that it is a social studies teacher. So my total is still 39. There's still 39 teachers, and of those 39 teachers, 8 of them are social studies teachers. So then I'm going to add across, and I end up getting 17 out of 39. Then you divide that out, and you get 0.436. Okay, so I didn't have to subtract anything there because it was a mutually exclusive event. So there's a 43.6% chance of that occurring. Let's take a look at number 6. So out of the 1,400 students, 550 take Spanish, 700 take biology, and 400 take both. Here's a hint. If in the word problem it says that there is a both portion that exists, if there's a both portion that exists, it has to be inclusive because it's telling us that someone could be taking Spanish and biology. So let's go ahead and let's first calculate out the probability of them taking Spanish. Well, there's 1,400 students, And of those students, 550 of them take Spanish. Then we're going to calculate out the probability of biology. So of those 1,400 students, 700 of them take biology. Now, here's the tricky part. Because it's inclusive, we have to subtract off that both probability. So I'm subtracting off the both probability. So of those 1,400 students, 400 of them take both. And we're subtracting that off because Spanish students are being counted here, and they're also being counted for biology. So that one student is being counted twice for Spanish and for biology. So we're subtracting off one of those by subtracting off that both portion. So 550 plus 700 minus 400 is 850 divided by 1,400. So you divide that out and you get 0.607. So there's about a 60.7% chance of that occurring. All right, let's take a look at number 7. So there are 2,400 subscribers to an internet service provider, 1,200 own HP, 500 own Dell, 100 own both. Again, because it's giving you that both portion, it's an inclusive event. So we're talking, we have 2,400 students. Okay, and so subscribers. So first thing I want to do is calculate out the probability that it's HP. Well, 1,200 own an HP. So that's my first probability. Then I'm going to calculate out the probability of them owning a Dell. Well, that's 2,400, and of that 2,400, 500 own a Dell. So that's my probability. Remember, just successes over total. Now, because it's inclusive, I have to subtract off the probability of it being both. And it tells us that there are 100 that own both. Now, here's a trick that students sometimes forget, is that when you are adding and subtracting fractions, you have to have this bottom number that is the same. And when you're doing mutually exclusive and inclusive events, your bottom number is always the same. And it has to be in order for you to add fractions. So when you add and subtract fractions, you're going to add the top and subtract here. So I'm adding and subtracting all of those to get 1,600, and then you go ahead and you keep the bottom the same. So 1,600 divided by 2,400, and then you get 0.667, or 66.7% chance of them owning an HP or a Dell. Let's take a look at number 8. There are 4 algebra books, 3 literature books, and 2 biology books. If a book is selected at random, what is the probability of selecting a literature or an algebra book? So you need to ask yourself, can you be a literature book and an algebra book? And no, you can't. So that makes this mutually exclusive because you can't be both. So let's calculate out the total number of books we have. We have 4 plus 3 plus 2. So that's 7 plus 2 is 9, so there's 9 total books. So first we want to calculate out the probability of it being a literature book. Well, 3 out of the 9 are literature books. Next, we want to calculate out the probability that it's an algebra book. Well, there's 9, and 4 of them are algebra books. So now, when I go to add this, I'm going to add 3 plus 4, which is 7, and then divide it by 9. 7 divided by 9 is 0.778. Okay, remember, I didn't have to subtract a piece off because we decided that you can't be a literature book and an algebra book, so there's nothing for me to be subtracting off. Next, let's take a look at number 9. So in the game of bingo, balls are numbers 1 through 75. The numbers correspond to a column. So those columns are shown, or what goes in what column is shown on that table there. So a number selected at random, what is the probability that it is a multiple of 4 or is in the O column? Are there going to be multiples of 4 that are in the O column? Absolutely there are. So this is going to be an inclusive event because it can be both. So what I'm going to do to help myself is I'm going to write out the multiples of 4. So I have 4, 8, 12, 16, 20, 24, 28, 32, 36. I know this is super fun, right? 40, 44. And I'm going all the way to 75 because the numbers are 1 through 75. 48, 52, 56, 60, 64, 68, 72. Now I can't go to 76 because there is no 76. It ends at 75. So if you were to go through and count up all of those multiples of 4, you end up getting that there are 18 multiples of 4. So you need to ask yourself, okay, how many total balls are there? Well, 1 through 75, there's going to be 75 total balls. So there's 18 divided by 75. So then what we need to do, now that I've calculated out the probability that it's a multiple of 4, I need to figure out how many letters or numbers are in the O column. We have 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75. So that ends up being 15 numbers out of the 75. Now, there are a couple that are included in both. So this 64 and 68 and 72 are being counted in this probability and in this probability. So what we have to do is we have to subtract. So we have to take and we have to subtract 3 out of the 75 because there's 3 numbers that are being counted for both. So then we're going to add 18 plus 15 minus 3, and that's going to give you 30 divided by 75, which gives you 0.4. So that means there's a 40% chance of you getting a multiple of 4 or that it's in the O column. Last but not least, let's take a look at number 10. A card is drawn at random from a stack of cards. What is the probability of drawing an ace or a face card? So aces are actually not considered a face card because they don't have a face on it. So you cannot be an ace and a face card. So this is a mutually exclusive event. So we learned on your probability kind of review notes how many numbers of cards there are. So I always suggest having that notes out while you're trying to do these card problems because it's there to help you. So out of the 52 cards, there are going to be 4 aces because there are 4 aces in a deck because an ace is a type of card. Then out of the 52, how many are face cards? Well, there's Jack, Queen, King, Queen. So there's 3 cards in each of the 4 suits. So to get the number of face cards, it's 3 times 4, which is 12. So there's 12 face cards. So now we can go ahead and add this. So 4 plus 12 is 16. 16 divided by 52. And you get 0.308. So that means there's a 30.8% chance of that occurring. So that concludes your note video today. Please make sure you get that Schoology quiz taken. Thank you for listening.